Welcome back for today. So yesterday we did the first steps about learning how our HPC system looks like, and that there are different kinds, like shared memory systems, distributed shared memory systems, and then complicated ones which combine both and add accelerators. And you heard a little bit about performance. But today we want to kind of get really into it. Yeah. So this afternoon we want basically you to really use Fukaku, write a little program, a parallel one, and run it on the computer. So before that, I have to teach you how to write a little parallel program. Okay. So before we start, can I have a quick hands-off? Who has written who can really program, has written programs in C, Fortran, or Python, just on a laptop? So I hope everyone. Okay, so who people who don't have so much experience yet, you probably in the exercises have to look for a table where there's one person who did it already and work together with him to do it, or follow carefully the steps. It's not too complicated. But yeah, but who is mainly using Python? Okay, most of you, which is not bad. Who is using C or no C? C programming? Not so much. Okay, good. Just for it, I know later for the afternoon how we can go forward. Okay, so now starting to the lecture. So what do you want to do today? So I will start, talking about parallel programming in general, a little bit. Then we talk about what do I do if I have a distributed memory computer? Yeah, so so it means, if I just have one computer, I just use C, Python as I use on my laptop. But now I have basically multiple computers connected together through a network. So I need to know how can I use these together, which means I have to go through the network, so it's across nodes, which is called intranode. And that basically means we're using a specific framework, it's called MPI, and I give you an introduction to MPI. Okay, starting with parallel programming in general. You saw some of that already yesterday, but just for repetition. What does it mean if we parallelize a parallel computer? So we take our sequential program, but then we have to change it that the data we are working on is distributed to the different memories of a computer, which is called data distribution. And you have to kind of write it in your program. And how to do this done, I show you. Then the calculations in our algorithms, we call it work. We also have to do a work distribution. So the different processors work on different portions of the data. Because if everyone is doing the same, we're just doing it 10 times and we're not getting any faster. Yeah? So you have to split up the different processors work on the different things. And then, we probably need some extra instructions that these different processors talk to each other, exchange data, synchronize, and so on. And as I said yesterday, if you want to really call yourself an HPC programmer or not just a parallel programming programmer, you have to do it to make the program as fast and as efficient as possible. And I showed this picture yesterday that we split it up, like making a whole, and then you have the work. It's like these are the processors basically, and we assign them to the data and they work on it. Okay, so so we basically have two things we need to worry about. One is the processors we have and the memory we have. And when I parallelize something, means that I'm distributing the work, the calculations, as I just said, among the processors. So different processors work on different portion of the data. And I have to synchronize this distributed work, so that everyone say, oh no, I'm done with the first step. Now everyone is done with the second step. So this works for all machines. If I have a case that the memory is distributed, we have a distributed memory system, we also have to distribute the data because there's more than one memory. Yeah? So we have, and then we need to also communicate between the local and the remote processors. And then there's parallel programming models, which basically give you methods or ways to express in your program how to do the distribution of work and data and how to communicate and synchronize. And this is called a parallel programming model. Okay, so now we go a bit further. We have to go a little bit into details of computer science. This can be a little bit complicated. If you don't totally understand it, it's not that bad, but perhaps you should, if you at some point fully want to understand it, you have to grab this concept. So, and there's two things in an operating system to allow us to run programs. One is called processes, and the other one called is threads. Both are ways to say, here's a set of instructions, and I run on a specific set of data. For a normal computer, just like a smartphone, laptop with one processor, so I call that sequential, like one, there's typically a process which combines everything together. So the process has kind of the set of instructions he wants to execute, and then he has data areas. And it's typically split up in 3 areas. There's the actual memory, which is called global static data. Then you have a stack. This is the name. Like computer science people probably know more what I'm talking about, which helps you having local data. So data which are just basically the parameters of a function or stored inside a function and not about for the whole program. And then you have a heap for dynamic data. So I need additional data, so you can say, oh, give me 10,000 more integers, so allocate and deallocate or malloc. This is a function. So we have these 3 portions, like the global data available for the whole program, the heap for additional dynamic data, and the stack for local data in the function or the parameters. So, and then process basically has one thread, and the thread is representing kind of the program, and so you have a list of instructions, and there's a way, say, this is the first instruction, this is the next one, then I go here, and go here. So we have like a path through that program, and it looks like a string, like a thread. And this is why I call it a thread. Okay, so this you have on every computer. If we have an operating system which supports multi-threading, then a process can have multiple threads. This means, I starting with one thread and I said, oh, now I need to do 2 things in parallel. I create another thread, and then you can work on both. Because they are together in one process, they have both the same heap and the global data. They can still work on the same memory, and they can still, like the dynamic memory I'm allocating, I can also using. But every thread can run its own functions, so we need different stacks which store the local data, the function local data. Okay, so in a parallel program, I can use these normal processes, the sequential processes with one thread on every processor, and then because they don't share data, I need messages to communicate between the different processes. Or if I have a shared memory computer, I can just use multi-threading. I'm starting one program, and then all the data is accessible to that process, and I can just use multiple threads to to work on the different portions. Yeah? Or you can combine both. Okay, so I try to visualize that a little bit. Yeah, so what I just said, just to repeat. So I have a section. Yeah, the problem with computer science is there's nothing you can grab, or it's everything inside the computer. It's just the concept. So some people call computer science the science of boxes and arrows. Yeah, all our diagrams are some boxes with arrows go from here to here. This is the next step. Okay, so basically here is the green portion. Think about this is like some portion of a memory which has all the instructions I want to execute. Yeah, and then I have some, basically it goes through and then there's a loop and then go through. And then it has the stack where I store local data. I also have registers in the processor. Then I have a heap for dynamic data, the global data, and also the files I'm opening and so on. And then this is on one processor, and the second processor I use the operating system to start another process. And then it has basically the same. Yeah? And what you often do is basically that you have one program and the code of that program is loaded here and loaded here. Yeah? They actually use the same program, but it creates two copies of it to run on the different processors. And then if I need to basically get data from here to here, he has to use a method to send a message which goes through the network, and then the other one is getting the data. Okay. If I have a shared memory program, yeah, I basically have that. So I start with basically one process, and then if I need more people to work on, I have here a command, create another thread, and then I can have multiple paths going, but because they are in one process, they can share the files, the global data, the heap. It's just that the registers and stack are separate for each of them for the local thing. Yeah, I think this is the most difficult slide in my presentation. So if you are new to programming, this might be overwhelming. As I said, it's just a pointer. Then at some point, if you want to become a master of programming, you need to understand that. Okay, so now parallel programming. How do I do that? Do I write different programs for every processor or so? No. What you're doing is, it's called SPMD, single program, multiple data. So, and every programming model in parallel computing is basically based on that. So you write one program, and that program gets basically executed in the different processors, and you write your program in a way that each process is working on a different portion of the data. This is basically the data distribution. Yeah? So you say you have a huge matrix, and then you say, okay, the first row is the first process is doing, the second row, the second process is doing, and so on. So everyone has the big matrix, but then in your calculation you say, okay, if I'm sum it up, yeah, everyone is summing up a different portion of a matrix. So the programmer writes one program which is executed on all processors, yeah, but they work on different parts of the data. That's the basic concept. And then, how do I specify, like, what are the different portions? So I need to know, if I have like 10 processes, which process I am out of these 10. Yeah? So, and what you typically do, I mean, everything is based on math and numbers. So basically each of these copies of the parallel program get a number. The first one gets number 0, the next gets number 1, yeah, and so on. And if you have like 100 processes, you have processes from 0 to 99. Yeah? And then there's some function in your programming model who says, oh, my process or thread identification is 42, then I'm doing this, otherwise I do something else. Yeah? So that's basically the basic concept. Okay, so now MPI, or distributed programming. Yeah, so I said we have multiple processors. I write my program, when there's a mechanism to load this program into the computer when we're executing it, and when each processor gets the instructions to execute. Yeah? And then each process has its own memory. So this is, I use slightly different colors here for the data. And as I said, SMT style. So basically, you have a program, and you work on your data, and your data means the data in the memory of your process. And this is called the local data. When I talk about local, it means the process is using the data stored in his processor, in his memory. This is local. And when I say I need data from something else, it means I have to go remote. So there's also a distinction between local data, which is my own data, and when the remote data on the other processes. Yeah? And of course, here it's just inside the process. I just use read and write for the memory, which is simple. But if I want to go to remote, it's always complicated. Yeah? I have to tell one, I need this. That person has to read the data, send it to me, and then I have to store it in my thing. So as I said, you have to somehow, in your program, explicitly write commands how to do this data distribution, how to communicate and synchronize. Yeah, and there's different ways of doing it, but meanwhile, everyone is using MPI. Okay, what is MPI? MPI stands for Message Passing Interface, and it's a standard. But it's not a standard like international, it's not an ISO standard or some Japanese standard, something so and so. It's just that all the universities, all the research centers, everyone who was interested in parallel computing, they got together, or they're still getting together, meeting from time to time, and then they agree how to do it together, so that not everyone has to do their own thing. So this is called a de facto or a community standard. And they started already in 1994. So 1994 was the first version, and then they added more and more things, and they are still working on it. So there's a new version came out basically just last November. And it's implemented as a library. Yeah, so as a library with functions, and then in my program, I just use the different functions out of that library to do the sending a message, synchronize, and things like that. And there is a version in the official standard for C, C++, Fortran 90, and Fortran 2008. There's unofficial versions, not documented or standardized in the standard, where people said, okay, I can make it also available for Java, for Python, Julia, and so on. Yeah? So if you basically like interested in Python, you can actually use this package MPI for Python, MPI for Py. And everything about MPI you find on that website. It's for free, so you can download the standard, which says, oh, this is all 600 functions and what they do. You can find links to tutorials. You can download examples and stuff like that. Okay, so as I said, MPI is huge, meanwhile. We're only looking at MPI 1, which is the basic thing everyone is needing. Yeah? And there's basically 4 groups of functions we need, and that's it. So you want to send a message from one processor to the other. Yeah? Like up here, processor 0 wants to send a message to processor 0. Yeah? So it's called point-to-point communication because it's from that point to that point. It's like sending a postcard. Yeah? So you said, okay, I'm processor 0, please send this to processor 0, and then on the back side you write, okay, here's the data you need. Then there's collective communication, which means a group of processes, like all of them, or like the left half, the right half, some group, they basically work all together on communication. And then it could be, say, like the one processor is sending a copy to everyone. This is like mass mailing or spam mail or advertising. Yeah? So like, here's some, whatever, something happening. Here, please everyone read it. Or someone is collecting it from everyone. When you need to synchronize, and this is barely a barrier, and I explain what it means later, and then we need to use something to kind of organize our group of processors, and this is called communicators. So basically, these are the 4 concepts you need to know. What's the point-to-point communication, a message, what's collective, what's a barrier, and what are communicators. And that's basically is all you need to write a simple parallel program, and which we will do in the next, hopefully, 30 minutes. Okay. Again, the most complicated construct is a communicator. It sounds more complicated than it is. If you don't understand it, just read the slide 3 or 4 times. It's not too complicated. So we need to talk about a group of processes. Yeah? So who's belong together? Yeah, you could say like, one group is this row, there's a second group, that's a group, and that's a group. Yeah? So you're group 0, group 1, group 2, group 3. But sometimes I need, say like this group needs to listen, task 1, and you need to communicate about listening, and when you do exercises, which is a different task, and you also need to basically talk to each other how to do the exercises. So when you're now communicating, you don't want like the postcards are going back and forth. You say, oh, is it about listening or is it about doing the exercises? So a communicator says it's a group of people doing a specific task. And this together is a communicator. And then, so it's a communication context. It says who is communicating for which purpose. And then there's another communicator. It could be a different group of people, but it could be the same group of people doing something else. Yeah, and the most thing you're typically doing is, so everyone is communicating like in your program. And then there's another group of people who gives you like mathematical library. Yeah, so how to do a matrix multiply or something. And they also want to use MPI to communicate the matrix multiplication, but you want that their messages don't get mixed up with your messages. Yeah? So as a normal programmer, use your communicator, all processes in your group, and then the library basically makes its own communicator, which are also all processes, but this way the messages for your program and the library gets separated. Okay? That's basically the basic concept. The next thing is, how do we start? Somehow I need a start to do that, and then basically for every MPI program, there is a communicator which is always there. You don't need to create it or something. So it says MPI world. So the communicator MPI world means all the processes for you working on the main program. Yeah, and so normally, as an example, as a simple way, everyone starts with using MPI world. Yeah, and then you have special things. You say, okay, the left half of a processor do something different than the right half. You can create a subcommunicator, it's called, by saying, okay, I want to have a new communicator which only have processes 1 to 5, and then I create another communicator with 6 to 10. Yeah? Okay. So this is either a type, like it's the name is MPI-COM, or type MPI-COM in Fortran and in C. Okay, and now we have a few functions, operations, which we can do with communicators. The first one is, I want to know, if I have a communicator, how many processes are in this communicator. Yeah, is it 8, is it 10? And then the second thing is you want to have your number. I'm the first one, the second one, and so on. And your number, your ID, is called a rank. Okay, and then you have functions to make new groups and communicators and so on. The most important point is, when I send a message, it's always inside a communicator. I cannot say, I'm sending a message to number 2, because there can be many number 2s if there's many communicators. You have to say, I'm sending a message to the communicator, like MPI conworld, the number 2 of MPI conworld. Yeah? And when you're doing a collective operation, you also do it on communicator, because it automatically goes to all the processes in the group of that communicator. Okay? Still following? Okay, perhaps you see an example when it's easier. Okay, so these are the 4 most important functions in MPI. Every program needs them. So you need to know at least these four functions, and you can ignore all 600 other ones. But with these ones, you can already write quite some programs. So first, basically, you have a function called MPI init. So you have your normal program, and now you want to do communication and synchronization between the processors. So you have to initialize MPI. You said, I want to work in parallel now. And it's called MPI init. Yeah? And you have to call it once time in your program before you're doing any other MPI functions. This has to be the first function. But you can only do it once. You say, now I'm doing MPI. Then you can call MPI functions, and when you are done, you say, MPI finalize. Yeah, there's no more messages, no more synchronization, I'm done. So everyone has to call it, the program has to call to need it at the end. Again, only once, after all the other MPI functions. Yeah, and then, as I said, I want to find out how many processors we are and which number I am. So is this MPI communicator size, which communicator, and this is an output variable, so it gives me back the number of processes in this communicator, and comRank gives me the rank, which is my identification. Okay? Okay, so here, I mean, if you have done programming classes at the university, we typically start with a hello world. Yeah, so the program is, you write on the screen, hello world. So what is the hello world of parallel programming? Yeah, because you have multiple people, you say, hello, I'm 5 of 10 people. Yeah, the next one says, I'm 6 from 10 people. Yeah, and then, so this is how you do, this is in C, how it looks like. Yeah, so everything in black is like normal C language. Yeah, I have a main program. I need variables for errors to store my rank and the number of processes. And when I print out, hello, I'm of so and so much. Yeah? Okay, and then we have to have MPI. So you have to add another program header, mpi.h, and then you call MPI init, and in C, you pass it the arguments of the program. Then you call MPI rank. With MPI conworld, we just want to use all our processes, the predefined ones. And because in C, it's an output parameter, you have to put this, what's that called, an ampersand in front of it. And then I want to know how many. So again, you say MPI conworld, the number of processes. Yeah? And basically, when it runs, it basically prints it out. This is the same thing in, oh yeah. So what happens is, so these MPI functions return an error if something goes wrong. But if you don't do anything really special and complicated, what happens is, if there's an MPI error, it just kills your program and stops. So even if you basically, because in that function, if there's an error, it just stops. You never get to the point that the error is returned. Yeah, so basically what all people do, they're just ignoring the error because you cannot do anything with it anyhow. And then it's a little bit simpler. But this is really advanced. You can do your own thing, but when you have to say what in the error, how do I recover and all of that. So in a simple one, you assume everything is working and you do it this way. Okay. This is the same in Fortran, but there's basically no Fortran people here, so I skip the Fortran. Again, this is Fortran, and here's the Python. Python is a little bit easier, as usual. Yeah, basically, you import from MPI for Pi, you import MPI, and then basically you get an MPI object, and from that MPI object you get the COM world, and then in COM, the MPI COM world is stored, and then on that communicator, on COM world, you use the method get rank and get size. And then you print it again, I'm from here to here. Okay? Okay, and here's some more information about Python. It might be, as I said, like there's a quite good documentation on this thing. If you're using Python, please look that up. Okay, then there's other language, as I said, there's for C++, Julia, Net, Java, and there's the names you need to Google to find it, if you're interested. Okay, assuming you have a C or Fortran program, so Python you just run, because it's interpreted and so on. But for normal languages, we have to compile it. And the thing is, yeah, like compilation means, oh, you have to specify where to find the MPI header file, you have to link in the MPI library and all that. To make it simple, basically all the MPI libraries provide special commands to do this automatically. Yeah, so like for C, there's typically a program called, a compiler called MPI which automatically links to the path where the MPI header is found and automatically adds the MPI library and so on. The problem is, every MPI library, it could be one from Intel, one from Cray, one from Fujitsu, they use slightly different names for the compiler. So this is the typical ones, but you have to look up like in the Vokaku documentation or your cluster documentation, oh, if I'm using this MPI on my computer, I have to use this command. And you can have actually multiple MPI libraries on some clusters. Yeah, there's typically a public domain one you can download from internet, and then there's one from a vendor. And yeah, you cannot use them together, so you have to choose one MPI and then use it. Okay, then I have my compiled program, and now I want to say, now run this program on 8 processors. There is there's either a command called MPI run minus NP for number of processes, the name, like how many processes you want to have, and the name of executable function. Or lately, there's also an MPI exec, but when it uses minus N in the number of processes. But again, this is not standardized. Yeah, I know like if you have a computer who uses the Slurm batch scheduler, you have to use srun. On Craze, you also have to use AP run, and so on. So the MPI standard says what are the functions, what arguments, what they do, but how to compile it, how to run it is unfortunately system dependent, and you have to find out. Okay, one important thing is, you see here is, when you run the program, you specify the number of processes. So it's not that you write a program which is good for running on 8 processes, but you write a program which can run on any number of processes. And you write your data distribution and communication in a way that it works for all number of processes, if possible. It's not always possible. Yeah, and then only when you run it, you say, now run this program with 8 or with 10. So when we go back for our hello world, we don't say anything, is it 8 or 10? But we use this get rank and get size functions to turn, oh, now I'm running with 8 processes and I'm number 10. Yeah? And you use these 2 numbers to organize your program. Okay, just give me a second. Okay, so now we have a distributed computer. So here's the different processors, here's the distributed memory, and it's connected through the internet, like as I explained you yesterday. So now I have my little process, yeah, it has the instructions, the thread, yeah, which calls init, the rank, size, printing out hello, and the finalize. Right? I just make a little icon here. And then I have on the, because they are local variable in the main functions, these are on the stack. There's two spaces for my variable, one to store the my ID and the numproc. Yeah? So now I use MPI run, and I said run it on n processors. When it does, the operating system takes this, copies the execution on each of the processors, and in each memory creates space for these two variables. So basically on every processor there is a different place to store the ID. And then if this processor calls my rank, he gets, oh, you are n-1, and it stores n-1 here. If that one is calling it, he gets return 1, and 1 is stored here. Yeah? So this is basically how this SBMD is working. You take the same thing, run it everywhere, and when you run it, it just works fine. Computer. Yeah? I have just one big memory and processes. What can I do? I don't care. I just ran the same program. The operating system creates processes, and it just uses the memory to give each process their own copy. I just ignore that's one main memory. Yeah? So it doesn't matter. So MPI works all the time. I don't have to care is it shared memory or distributed memory. Yeah? It basically, it just basically works in each way. It ignores basically that there's a shared memory. It's not exactly ignoring, because if I'm sending messages in such a system, it knows, oh, it's a memory. So it just copies data from here to here. And if it's in a distributed memory, it sends a message through the network. But you don't care. Yeah? This is basically hidden by the MPI library. Okay, next thing, I'm running my hello world example. Yeah? And I guess everyone expecting you get something like this. Hello 004, 104, 204, 304, if I run with 4 processes. But this is parallel computing. Yeah, it's like the same thing if I use 4 people. Who is the first? Yeah, who is the fastest and the slowest? Who is lazy? Same thing. Not every process is the same. Yeah, so you could get, oh, 304, 104, 204. Because you didn't specify the order. It's just basically how it comes out. Or what also can happen is, so here you get a nice line, but on some systems you just get everything at once. And you get kind of these bloop out of it. Yeah? And then it's even more funny, if you do the same thing with Fukaku, you don't get anything. What happens is, yeah, because on very large computers, it's like, there's this huge computer, and you cannot connect all these processors to your screen to route the output to your screen. So what it actually does is it creates a file for every rank. So like in the directory, you're running the program, it's creating a directory, and inside the directory, for each output channel, it creates another directory, and in this channel, it creates a file for every rank, and then we have to basically look at all the files to see the output. So what do we learn from parallel programming, especially from this? It doesn't make sense to print something on the screen in a parallel program. Yeah? What you typically do is you're creating file, and then writing into that file in a coordinated fashion, in the order you want. And then after you run your program, yeah, like you look at the file, what came out of it, yeah? Okay, a little bit, I skipped that. So this is advanced. So how I would send messages. We don't have a time here. I'm looking more into now, which is easier, and we also will use it in a little example, how to do collective operations. which means basically using all the processors at once. So one is, the simple one is synchronize. You basically want to make sure everyone in your group is done with a specific task. And that is called a barrier. So so basically a barrier is like when you enter a parking lot, yeah? So you close the barrier, and you wait until everyone is here, and when everyone is here, you open and everyone can continue. Yeah? And this is basically everyone in your group of processes is calling this barrier function, and when we are stuck inside the barrier function, until MPI knows everyone is there, and when you return and when everyone is continuing. In this way, you can ensure everyone is at the same spot. Okay, the next simple function is, I want to basically have a group of processes. One process has some specific data A, and he wants to that basically everyone knows about it. It's called a broadcast, like in radio. Yeah? And this one process, it doesn't have to be the 0 process, it could be also 2 or 1. The idea of that is called the root. Okay, and then basically I'm saying, yeah, distribute some data with A from the root process to everyone in the process group, which is the communicator. Yeah? So I say, like here, in this case, like this is MPI world. So we would put in here MPI world. Here we would put number 0 because root is the first process. And then we have to what to send. And then basically we have to specify where is the data located in the memory. So normally this is the name of a variable. Yeah, because the name of a variable stands for that location in memory. Yeah, so, and then we cannot just send like a number or a character, but we can also say, oh, this memory, like this variable contains like 1 integer or 5 floating points. So we can also send a whole vector of data at once. Then here's another situation. So like here, the process has a vector of data, and then basically the first element in the vector goes to the first processor, the second, so you kind of split things out. Yeah? So you basically, A goes to the first one, B goes to the second one, and C goes to the last one. So this is called scatter, and if you're basically doing the other way, yeah, you're collecting these, and then one process is basically getting a vector of the copies, then it's called a gather. Yeah? And then with the operations is, you say, the inputs, like what goes in, what goes out, and again, who is either the root sending or collecting. Yeah, so this is send, and so this is gather. And then there's another one which is very useful, reduce. Yeah, so basically again, it's like gather, but instead of getting a vector of all these, basically you get like the sum or the like the product of everything, or the minimum. Yeah, you say basically how to take that, and then basically I want to get the minimum of these values, and this one just gets the minimum out of these, or the sum. And this is basically done with reduce, and in addition you have to specify here in op, basically, here in op, what is the operation for reducing everything together, and then there's an all reduce that not only the root gets it, but that everyone gets the minimum sum. It is called all reduce.